hello big hands. We are now in the final stretch of this course, a course that, looking back, we can say has been quite intense and also quite satisfying, I think. Don't tell me you haven't been moved, that you haven't gotten goosebumps, that you haven't felt like crying with emotion over things as beautiful as resonance and things as common as forced oscillations. I know it hasn't been easy to understand, but every damn second was worth it, I'm sure of it. But at this point, after having climbed the great peak of knowledge in oscillations, not without great effort, I don't know. It's time to enjoy the view and finish the course at a different pace. Like in the Tour de France, right? They climbed the Tourmalet in the final stages, and after that, well, what's next? Well, they take a walk along the Seine, right through Paris, in a much simpler and more relaxed event. Well, just like us, we've already climbed the Tourmalet, and now it's time to descend slowly, enjoying the views, calmly, watching how the breeze blows by the Seine. In short, we're going to slow down a bit and enter a mode of enjoyment for physics with a very appealing and less dense topic. Today we're going to take a peek above the world of waves, the big sister of oscillations. And I promise this is going to be simpler, not as dense, not as intense, it won't hurt as much. And again, we are dealing with a topic that is not abstract, not far from our human experience. In fact, there might not be anything as ubiquitous, omnipresent, mundane, and everyday as a wave, because they truly are everywhere. Waves are the sea waves, the vibrations of a string, sound, light, flags waving in the wind, the hair of your beloved. There are waves in cell phone signals or in electronic circuits. I've even gotten poetic, you see, it's something fascinating. So what I'm saying is that we are surrounded by waves. See, people are not exaggerating when they say the world is made of vibrations and waves. And the truth is, the world looks quite different the moment you start to understand this very common phenomenon, but from the perspective of physics and mathematics. And I ask you to pay close attention, because since these things are so important, waves appear everywhere, in all the subjects you study in physics. And not only in physics, in engineering, in chemistry. Yes, you learn it once and you learn it for good, it stays with you for life. An effort today is something valid for a lifetime. So let's go for it. Let's dive into the world of waves, the big sisters of oscillations. And why do I say they are the older sisters? Well, for a very simple reason. Look at this, a particle going up and down, simply because you are pulling it by the hand. Well, by now you already know what's happening. This particle is oscillating and we already know how it does it. Mathematically, we have the harmonic function over time. But now we are going to do something very fun. Let's attach a second particle to the first one with a thread. As the first one moves, the second will also oscillate, but with a slight delay. It is dragged by the movement of the first. It is being influenced by this oscillation. So now we do what you are probably already imagining. We add a third particle, a fourth, a fifth. All of them are influenced by the movement of their neighbor, and therefore successively by the first one. And in the end, what do we have? Well, the entire string is vibrating. We have created a wave. Well, a wave is nothing more than this, a movement, or more generally, a magnitude that propagates in space affecting its neighbors. And I say magnitude, because in this case, well yes, it has been a movement, but there are pressure waves in the air, electricity waves, even gravity waves. In the end, a wave is anything that can propagate through its surroundings by contagion in space. And here comes one of the important points. In the wave, if you notice, nothing is physically traveling. There is no net movement or net transport of matter, it is pure energy that travels and spreads. Moreover, the wave is not at any specific point, it is energy that spreads through space. Only that. And yes, friends, at this point I have very good news, because conceptually you have already seen it, it has been easy. I know it has been. This is not like the energy chapter where we had to imagine abstract things and then mathematically what's up. That requires, well, it's something that more or less everyone can grasp, right? But also mathematically, it will be very simple, and all because of a detail that you might have already grasped. The wave is formed from an oscillation in time, which generates an oscillation in space. That is, it is a harmonic movement in time and harmonic in space, doubly harmonic. And since we already have the mathematical treatment of oscillation, we already have all the work done. We just have to copy what we applied to the oscillation in time and do it in space. Okay. If this is an oscillation in time, I change time for position, and this will be an oscillation in space. And then, after this, I can combine them. Because this is a static frozen oscillation, it does not vary with time. For the wave to move and propagate, the temporal part is needed. We combine them. And now we have this here, the equation of a wave that propagates in space. In fact, notice this detail. If we look at the point x equals 0, we see that it moves with harmonic motion, it oscillates. And the same happens if we look at any other individual point. Each point oscillates vertically over time, but together there is also an oscillation in space. Very beautiful. In fact, there's another way to understand it, in case you want another perspective. I have a function, whatever it may be, f of x. If I subtract an amount, the effect is to shift it to the right by that amount. Okay, so if I subtract a larger amount, it shifts more. And if it's larger, then even more. If you notice, what I'm doing is making that function travel to the right. And this is precisely a wave, something that travels in space, a disturbance that moves in space. Well, if I make that amount a shift to the right depend on time in this way, then we have something that travels in space, a wave, and this thing that accompanies time will be something like a propagation speed of that thing, which for the harmonic case would be like this. Well, that's all, friends. It's that simple. There's nothing more. Now, we just need to identify a couple of details and we're done. Look, just as the temporal part in oscillatory motion is accompanied by a factor that is the angular frequency, the spatial part will also be accompanied by an analogous factor, but for the spatial case, it is a kind of spatial angular frequency. Let's pause for a second on this point because it is important. The angular frequency tells us how many cycles occur per unit of time, or in other words, the distance between peaks in time, right? Well, this new spatial angular frequency will tell us how many cycles occur per unit of space. What is the same? The distance between peaks in space. We will call that new parameter, that angular frequency in space, the wave number. And notice one more detail. What goes inside the scene never has units, it cannot be meters or seconds, they are radians, they are angles. That is why, in the case of oscillations, we have a time magnitude. The accompanying parameter has to be an inverse of time, an angular frequency. That's how we define that W. That's how we W as 2 pi over a time, the period. Well, great. The same thing happens in space. What is inside must have dimensions of an angle. Since x is a position, that is distance, k will be the inverse of a distance and multiplied by an angle. That is, it will be 2 pi, the angle, divided by the distance between peaks. The distance between peaks is a very famous value. It is used a lot in physics. We call it wavelength. So we have everything now. The x is always accompanied by the k, the wave number, which is the equivalent of the w in space. And just as the w is related to the period 2 pi, the wave number is related to the wavelength 2 pi. Finally, we had seen that this factor with time in the harmonic function also has an interpretation of velocity. Well, let's use this explicitly. If instead of putting it this way, we put it this other way, we make the role of v, the propagation speed of that wave, explicit, identifying with what we had before, and we have it. Kv is that omega, is w, and this other form, with v written explicitly along with t, which is also very common when working with waves. And one last detail, and we're done, promised. This is a wave that moves along the x-axis to the right. Well, this is a wave that moves along the x-axis to the left. And this is a wave that moves along the y-axis to the right. And in general, this is a wave that moves through the 3 dimensions, moving away from the origin of coordinates. And now, friends, we have everything. Wasn't it as easy as I promised? Wasn't it? And enjoyable. It's nice to learn something so common and at the same time so useful, visual and tangible. Long live oscillations and long life waves. Finally, to wrap up this course, we move to the last chapter, which will be dedicated to some very common examples of waves. Ready? See you in the next video. See you soon.